Well, hello everybody. My name is Simon Foster. I'm a postdoc from the University of York, and I'm very pleased to be speaking at this year's online version of FormaliSE. I'm going to be speaking today about formal model-based assurance cases in Isabelle SACM. This is a joint work with Jakub Namucci, who's a postdoc at the University of York, and also my collaborators from D-Risk Software Systems, Colin O'Halloran, Karen Stevenson, and Nick Tudor. And today I'm going to be talking about a case study that we've been doing in assurance using Isabelle based on an autonomous underwater vehicle. So I'll first give some background and motivation. I'll then describe the AUV case study in more detail and show how we have applied formal model and assurance to it. So the purpose of safety engineering is to develop safe systems, and this is typically done by a number of processes, such as hazard analysis, risk assessment, determining causal events, and so on that may contribute to hazardous behavior, and trying to ensure that such behaviors are adequately mitigated. And to show that a system exhibits this, this concept of an assurance case was developed at the University of York and is well used in industry, I think it's fair to say. An assurance case is a structured argument supported by evidence intended to convincingly justify that a system satisfies certain desirable properties for application in a specific operating environment. These assurance cases are used to convince a regulator or other stakeholder that you have indeed shown that your system is safe. So for instance, if you think in terms of certification objectives, which can be provided by international standards like DO178C or ISO 26262, an assurance case allows you to show how you have satisfied those objectives and therefore why your system should be allowed in the air or on the road or wherever. Now, assurance cases are typically presented using a visual notation, such as the goal structuring notation or claims argument evidence. We'll be looking at some of those as an example later. Now, for assurance cases, formal methods are extremely valuable. They can be used to provide evidence, of course, through formal modeling and verification. But it's important to remember when we use formal methods that the evidence that we provide is always contingent on the fact that our models somehow reflect reality. So for instance, there's a supplement to DO178C called DO333 and that shows how formal methods can be used to provide evidence to satisfy the 178C certification objectives. And it requires you to argue things like that a formal method is adequate to model the particular kind of system that you want to, and that the model has been validated and so on. So the benefit of assurance cases is that they allow you to convey why this is the case. They allow you to put formal methods results in context. Now, an issue with assurance cases is that they are often manually created, and therefore there's a need for greater automation for them to ensure that they can be easily maintained and also evolve through the life of the system. And so this work is trying to look at how we can do a better job of automating assurance cases. And the particular piece of software that we are using for assurance case automation is Isabelle. You might have heard of Isabelle, that it's a generic proof assistant, and indeed it has been very successful in this area. It's been applied to automated program verification, and some success stories include, of course, the famous SEL4 microkernel, and also PikeOS, which is a real-time operating system. However, Isabelle also provides a lot of other features now, which make it amenable for assurance cases. So for instance, it has a machine check document model with an extensible parser whereby you can create new commands and new parsers for these commands and processing in the background for those. It has real-time syntax and type checking, and this allows you to do change impact analysis where as you're typing into Isabelle, Isabelle is checking to see, well, what impact will this have on other entities that depend on this entity that I'm redefining. Isabelle also allows us to add additional grammar categories, and this allows us to support a variety of domain-specific languages, so that Isabelle really allows us to integrate lots of different formalisms together. And as well as formal content, it also allows access to non-formal content. So Of course, you can write comments around things, but more than that, you also have a quite sophisticated text processing engine whereby you can write marked up text, and that marked up text can refer to formal content within an Isabelle document, and we'll see how that works later. And this just allows an extra level of integrity. And finally, it's very extensible, allows you to write plugins that can interface with external tools like automated theorem proofs and SMT solvers. And for this reason, Eclipse is ideal, we think, as an IDE for integrating a variety of formal methods, and therefore an ideal platform for doing assurance cases. And we'll see more about that later in this talk. Now, as I mentioned, we're going to be doing some modeling of an autonomous underwater vehicle, and the particular notation that we're going to be using to model this is a language called RoboChart. Of course, a very important part of being able to do formal methods is that we can present accessible notations to engineers that they can engage with. And so RoboChart is a graphical language which follows a UML style. And therefore is easy to understand, and yet it has a formal semantics as well, a complete formal semantics for the language, which means that we can apply a variety of analyses to the models that we create. There's two principal notations inside of RoboChart. There's first of all an architectural language, which allows you to describe blocks and connections between them, and also a state machine language, which you can see on the right there, where you can have states and transitions and events that trigger those transitions and conditions on those transitions and so on in the UML and SysML style. There's a very good tool for drawing RoboCharts called RoboTool. There's a link there at the bottom. And as I said, we can do formal verification, and in particular in Isabelle, we can do symbolic property checking via theorem proving. And this means that though RoboChart is very complex and it can have lots of different data structures associated with variables and with events, we can nevertheless check properties of it, even though it's infinite state, through symbolic techniques in theorem proving. And so we'll say more about RoboChart later. Back to Isabelle. So in order to represent assurance cases in Isabelle, we've created a tool called Isabelle SACM. This is a textual interactive assurance case language based on an OMG standard called the Structured Assurance Case Meta Model. This allows us to embed arguments into Isabelle and combine them with formal verification evidence. And so we can do machine checking of a safety argument and check that any evidence that we have does indeed hold that Isabelle can verify it. So this over on the left is a typical GSN fragments. This is goal structuring notation, and you notice that we have sets of claims, right? So the rectangles, these are claims. The system is acceptably safe. And how are we going to show that? Well, we're going to support this, which is what this arrow means. We're going to support this by a further claim. All identified hazards have been mitigated. This, of course, makes use of some context because we need to know what all identified hazards are. And so here we have a contextual element called the hazard log. So this arrow here means in context of. And then we break that down further into an argument over all identified hazards. And then we have two further claims which we need to satisfy. And the first of which we're going to support by some formal verification result. And so the aim of an assurance case is to break down claims piece by piece until eventually we can show how each of the claims can be satisfied by evidence, which are these circle nodes here. And this claim hasn't yet been fully satisfied, which is why you've got the diamond there. So this is kind of a work in progress. Now, Isabelle SACM allows us to represent this kind of argument structure in the language in a textual format. And so what we have here is a sequence of commands in Isabelle that precisely represent this structure over here. So we have claim C1, we have claim C2, and the text that goes within it, which is essentially unstructured text, although can refer to formal entities. So we see an example of that here. So here we have an inference. So the inference I1 here corresponds to this arrow, the supported by arrow. and it's saying that claim C1 is supported by claim C2. Now, these funny brackets here, these are called anti-quotations, and this means that we are inserting a link to a particular kind of formal element, in this case a claim. Right, and so what happens in the background is, so this is unstructured text essentially, but within it you can have these anti-quotations, and these anti-quotations will be checked while the Isabelle document is being processed to make sure that they exist, that they have the correct type, and so on. And if they don't, you get an error. And this then allows us to represent the argument structure in Isabelle as we do on the left. And so that's what Isabelle SACM is all about. So we're going to be using that in this talk for the autonomous underwater vehicle. So the overview of this paper is an investigation into the use of Isabelle to assure an AUV. To do that, we've extended Isabelle SACM with both terminology and requirements, so that we can encode requirements and show how they've been satisfied. We've also mechanized the SI unit system, and this allows us to support specifications with physical quantities, right? So like things like meters per second and other units that you may have there. We've developed a RoboChart model of an AUV safety controller. And we hope that our paper shows that using Isabelle, we can achieve much greater automation for assurance cases with integrated formal methods. The overview of our approach is here. So you have terminology, you have requirements, you have a data model, an architecture, and a behavioral model, all specified in RoboChart. And then you're going to use these, and you're going to integrate these into an assurance case in Isabelle SACM, together with an argument or a series of arguments showing how each of your requirements is satisfied. You can then use the Isabelle document preparation engine to generate a certification document, which will allow you to show to a regulator how you've satisfied your objectives. So let's look at this in more detail. So the particular case study that we're looking at is an autonomous underwater vehicle. And this is being developed by a consortium, including D-Risk, our industrial partner, and it's based on the Blue ROV platform. It's targeted at underwater maintenance tasks. So these things will run about in a pond, and they will search for things, perhaps pick them up or manipulate them in various ways. The AUV can be under operator control, or it can function autonomously. And obviously, when it's functioning autonomously, it needs to ensure safety, and it needs to demonstrate regulatory compliance, because these things can come into contact with humans and other AUVs. And so the kinds of hazards that we're looking at are collisions, but also the potential for causing things like splash, right, which might cause harm to the people around the pond. So D-Risk have supplied us with a set of system safety requirements that we have then endeavored to implement in an Isabelle-based assurance case and show how they've been satisfied. There are certain zones where the AUV cannot be autonomous, and these are called object proximity exclusion zones, and we need to make sure that they don't operate there. So the particular component that we are focusing on is something called the last response engine. This is a safety controller for the AUV, and it assures safety in the presence of non-verified components. So the idea is that even if your path planner, for instance, fails to spot a potential collision, the LRE won't. The LRE is assured to a high level of integrity, and so it will not allow a collision or other dangerous event. So it operates in 4 principal modes. You have operator control mode, where the operator has got responsibility, main operating mode, where it's operating at full speed autonomously, high caution mode, where it's getting close to obstacles, and collision avoidance mode, where it's detected a collision and it's trying to avoid it. So what does the LRE do? Well, if it's not under operator control, then what it will do is it will look for the next waypoint and set a speed and heading set point, which will pass on to another component called the autopilot that actually drives the actuators and would be represented by something like a PID controller. The software for the LRE is being developed under DO178C, and so it's very important to be able to show that we can satisfy the safety objectives and safety requirements. So just as an example of the sort of requirements that we're dealing with, here are 4. So you can see we're dealing with things like physical dimensions. we're dealing with things like mode switching as well. So like this when and only if when in OCM, the LRE shall accept operator control inputs and send them to the autopilot. So this is the situation when the LRE is passive, where it's simply passing on operator commands to the autopilot. This one is referring to the situation when you need to enter high caution mode. And this happens when you're getting close to a static obstacle, but not sufficiently close that you're going to have a collision. But the decision has been made that to mitigate against potential accidental collisions, that the AUV should drop its speed. And this is illustrated here. Right, so here's the AUV, it's passing along and it's going to go through this 300mm safety bubble, where this is the obstacle here. And when it does, it will continue going, but it will drop its speed. It will enter high caution mode until it exits the safety bubble, in which case it can return to full speed. And when it's at high caution mode, it drops its speed to 0.1 meters per second, where the normal speed is 1 meter per second. Okay, now let me tell you about how we have modeled this formally. So as I said, we're modeling it in RoboChart, and this is a representation of the architecture in RoboChart. So RoboChart provides modules, and these modules can have different types of elements inside of it. And in this case, we have a robotic platform, which is this block here, and this provides sensors and actuators that the controllers can make use of. In this case, there are 3 controllers that we're representing, which are connected to each other by a variety of ports. So we have the operator, and the operator can request headings, and it can request a mode switch by rec OCM, rec MOM, and so on. And it can also request a velocity. And the LRE is here. We'll look at that in more detail. Well, what it does is it passes instructions to the autopilot controller, which is down here. So it advises a heading and it advises a velocity. So then in terms of modeling this in Isabelle SACM, we first of all need data structures to be able to represent the state space. And this is an example of one of them. So this is a kind of Z schema-like notation that we've developed in Isabelle. And this allows us to specify the different variables that are available. So in this case, this schema is specifying some of the sensor inputs that you have, and these are the sensed inputs of the AUV itself, right? So you have things like the current depth below the water surface, you have the north-south velocity, you have the east-west velocity. So we split them into those 2 components, and you also have the rate of climb, which is the speed that it's going up or down. You'll note that these attributes can have both a numeric type and also a unit type associated with them. So as I said, we've mechanized the SI unit system, and this allows us to check whether units are correct, in as much as we should not be able to compose together values which have different units associated with them. So this allows us to have an extra level of integrity by having these explicit SI units in there. We can then model the behavior of the LRE, and this is a RoboChart state machine. So you can see you've got the 4 modes: OCM, MOM, HCM, and CAM there. And there's a lot of transitions explaining when we can transition from one state to another. And these are reflective of the requirements that DRISC have given us. So let me maybe outline one of them. So let's look at this transition here. So transitions are decorated with this kind of expression. You'll recall at the architectural level that rec MOM is an event which is an input, a channel input to this particular controller. And so what this says is when we receive this event, we can make the transition, but we also require there to be a condition that holds. And this is what these square brackets are. So the LRE has a number of internal variables. It has its velocity, and it has its horizontal and vertical velocity, which you saw represented in the previous slide. And so what this says is that we can only transition from OCM to MOM when the velocity is less than or equal to 0.1, the distance to a dynamic obstacle is greater than 7.5, and the distance to a static obstacle is greater than 0.3. So this is this safety bubble that we talked about. And in addition, we mustn't be in an OPES. So the intuition here is the operator wants to hand over control to the AUV, but it can only do so provided the AUV isn't moving too quickly and it's not close to obstacles and it's not in an OPES. Right, so this is the idea. And then we have a lot of other transitions that represent the other possible behaviors of the LRE. Now, what we can do in terms of assurances, you can take this RoboChart state machine and you can embed it into Isabelle. Right, so this is an Isabelle command that we've developed, which allows us to represent the state machine there. And underneath, a formal semantics will be given to this. So the idea is you draw your diagram in RoboTool. You can then translate it to this kind of representation. By the way, note the units again. So our variables and our events, which are specified here and here. So these can have units associated with them. We've got the different states, OCM, MOM, HCM, and so on. And the transitions down here, and the initial transition OCM is there. So under the hood, this will generate a formal semantics in a process algebraic language called Circus, and the resulting symbolic transition system can be used to support verification of infinite state systems. So we can use this to verify properties such as deadlock freedom, but also more specific requirements. We'll see an example of that in a little bit. But you see, the thing is that once you've embedded your formal semantics into Isabelle, now we can actually start to create a model-based assurance case. And this slide is really showing how all these different notations play together. So we have a requirement command, which is here, which is encoding one of those requirements. So what's it say? So main operating mode, maximum speed. On entering MOM, the LRE will advise a maximum speed of 1 meter per second. Right, so that's the requirement we want to satisfy. And then we're going to show how the state machine satisfies that using a claim, and the claims are shown on the right. So let's see how this works. So over here we have a claim which is saying requirement blah 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 is implemented by the entry action of state LREBEH MOM. So LREBEH is of course the name of the state machine, and MOM is the name of one of the states. And you can see that we have this here. So what this claim is effectively doing is it is linking this requirement to this state within the state machine. So this allows us to argue why our model satisfies the requirement. So it allows us to express traceability. And we've done this for several of the requirements. This is just a fragment here. So here we are showing that how 3 of the requirements are satisfied. And then you would have a top level claim, which is here, which shows that all of the LRE requirements are implemented in the state machine. And you have an inference showing that the 3 requirements support this top level claim. Right. So this then shows how we can use a formal model to satisfy requirement claims and make that explicit, right? So this is something that you could very clearly show to somebody that yes, all of my requirements are indeed satisfied. As I mentioned, you can also do verification. And so here we've got a theorem of deadlock freedom. I won't go to that in much detail, but we have automated tactics that allows us to do that. And effectively what this is saying is that there are no transitions in the state machine where there isn't an enabled transition. And this is because, for example, the operator can always request control. So you never wind up in a state where you can do nothing. And again, even though the LRE is infinite state, we have symbolic theorem proving, and so this allows us to overcome this. So you can see that we can really bring together a lot of different techniques here together in Isabelle. We can do assurance arguments with claims and so on, but we can also do very low-level formal verification. So in conclusion, our results indicate that indeed Isabelle can be used as a platform for assuring autonomous systems. We can embed assurance cases into the Isabelle document model, and we can integrate and verify a variety of heterogeneous artifacts. Obviously in this paper, all that we've shown is one kind of notation, which is state machines, but there are lots of other notations that we can also integrate. And we do this by using something called unifying theories of programming, which is a semantic framework created by Hoare and Hay that allows us to integrate lots of different semantics together. And this is supported in Isabelle by a large and growing library of mathematics that we can put to work in verification. So in terms of ongoing and future work, well, we want to be able to link Isabelle SACM with a graphical assurance tool. Ultimately, we want it so that we can write down these argument structures, not textually, but in a graphical editor supporting GSN or similar notations. We're also working on formalization of other parts of the AUV. So we're looking at the autopilot component. So this is the PID component, and looking how we can verify that along with the dynamics in differential dynamic logic, which is a deductive logical system for verifying hybrid programs from Andre Platzer that we've been working on integrating into Isabelle. And also we want to integrate a full hazard analysis and complete the safety argument so that we can really show from the top level claims of the various hazards that exist, how those hazards have been mitigated. So that's all I want to say. Thank you very much for listening. This work is funded by the Engineering and Physical Researchers Council in the UK. My project is a fellowship project called Sci-Fi Assure, which is running until June of next year. And we're very grateful to the EPSRC for funding this research. And if you'd like to know more about this, there's a URL on this web page. But otherwise, thank you very much for listening.